These are going to be our notes on Newton's method. Newton's method can be used to find numerous things out about a curve, but we are specifically going to look at using Newton's method to approximate the zeros of a function. And just as kind of a vocabulary check, when we talk about zeros, there are actually multiple ways that we can refer to zeros. Zeros are also known as the solutions of an equation, the roots of a function, x-intercepts of a graph. All of these things are considered zeros of a function. So lots of different ways to refer to them. So let me give you a big picture of what Newton's method is going to help us to do in order to approximate the zeros of a function. Okay, let's say for a moment this is the function at which I am looking, and I am going to try to somehow approximate the zeros of this particular function. So again, when you're talking about a graph, what we mean by that is I want to find the x-intercept right here. So let's call that x comma 0. Because this is an x-intercept, it'll have an x-coordinate of some x value. In this case, it happens to be a positive x value, but it doesn't necessarily need to be so. But its y-coordinate is going to be 0. If I want to approximate that, what Newton's method starts out with is it says pick an x value that you think is somewhat near this particular 0 or this particular root. And let's say we pick, let's do this one. Let's say here is some x value, and I'm going to call it x sub 1 because I don't want us to confuse the x values. Here is x sub 1. I think it is pretty close to the root of this function. Okay, well, what Newton's method wants us to do is to find the y value on the curve for this particular function. So that dot right there has coordinates. Its x-coordinate is x sub 1. Its y-coordinate is f of x sub 1. Okay? And at that particular point, what we're going to do is we're going to find the tangent line to this curve at that particular point. Let me draw that in. So here's a rough sketch of the tangent line to the curve at that point. And once we have that tangent line, what we want to do is then find the 0 or the root or the x-intercept of the tangent line. And that should actually be much easier than finding the root of this function, because this function, remember, it can have a relatively nasty equation associated with it. But this is a tangent line. It's linear. In general, finding the x-intercept of a line, it's not that hard. You just plug in y equal to 0 and solve. And in a linear function, that's pretty easy. So I'm not going to do that algebraically at the moment. We'll talk about the algebra and how all this works. Right now we're just trying to get a big picture. So let's say I find that 0 of that tangent line, call it x sub 2. You then basically repeat the process. You say, okay, if this is x sub 2, find the y value associated with that x value on the curve itself. Oops. So this point right here, the green point, has coordinates x sub 2, f of x sub 2. And you find the tangent line at that point. Well, notice that is going to bring it a lot closer. If we do the process over again and we find the x-intercept of that tangent line, notice how much closer we're getting to the actual 0 that we're trying to approximate. Let's say we're here at x sub 3. So again, you just repeat the process. Here's the point. Here's the tangent line, and notice we are getting much closer. So that is big picture how Newton's method is going to help us approximate the zeros of a function. Let's take a look at some of the algebra that's going to go on behind this. So let's lay some of the foundations. So first of all, some things that we already know. In general, if you want to talk about the slope of a tangent line to a function at a specific point, and that point would have coordinates x sub 1, f of x sub 1, so there's an x value and a y value, the slope of any tangent line is the derivative at that particular x value. So the slope of the tangent line is f prime evaluated at x sub 1. We already know that from previous sections. So when you want to talk about the equation of that tangent line, we've done this many times. We have found the equation of a line tangent to a function at a specific point. What we do is we find the derivative that provides us with our slope, and then we use the point slope form of a line, which usually you see that written as y minus y sub 1 equals m times x minus x sub 1. Now we're going to change that up just a little bit in that instead of saying y sub 1, we're going to say f of x sub 1, but that's just function notation. And then instead of saying m for slope, we're going to call it the derivative evaluated at x sub 1, because this is specifically the tangent line. So this is how we write the equation of the line in calculus. So what we want to do is we want to use this equation of the tangent line to see if we can find some kind of relationship between these x sub 1s and x sub 2, for example. Remember, x sub 1 was the first x value that we picked that we thought would closely approximate our 0, and x sub 2 was the 0 of that tangent line from the previous slide. So we're going to make use of the fact that when we want to talk about this x sub 2, it is an x-intercept. It is a root. Therefore, it's going to have coordinates x sub 2, 0, because it sits on the x-axis. So this is now a second point on our tangent line. One point on our tangent line is this x sub 1, f of x sub 1. So the second point is x sub 2 and 0. So what we're going to do is plug in x sub 2 in place of x, and we're going to plug in 0 in place of y. And then we're going to manipulate this a little bit. And this is what it's going to look like when we do that. So there's our substitutions. In order to figure out what kind of manipulations we want to do to this, keep in mind what we're trying to do is get some information about this x sub 2. Okay, x sub 1 was our guess, and what we're trying to establish is, okay, once we have our guess of x sub 1, what does that tell us about x sub 2? So I'm actually going to solve for x sub 2. So I divide both sides by the derivative of f at x sub 1, and then we're just going to add x sub 1 to both sides. So what this tells me is that once I've figured out x sub 1, once I've made that guess, in order to calculate x sub 2, all I have to do is take that x value and add to it the y value associated with that x value divided by the derivative evaluated at that x value, which is a cute little formula, but not necessarily helpful if, let's say, I want the 10th approximation or the 40th approximation. So we want to look for a pattern. Well, notice this is what I got if I knew x sub 1 and I wanted to calculate x sub 2. Well then, it would follow that then if I just wanted the third x value, the x sub 3, if I follow the pattern, then all I would need to do is take x sub 2 and add to that the y value associated with x sub 2 divided by the derivative evaluated at x sub 2. I basically just reused the formula. Well, if that's how I would find x sub 3, guess how I would find x sub 4? I'd take x sub 3 plus f of x sub 3 divided by f prime of x sub 3. So we use that pattern. And what we find is that in general, anytime you want the next x value, and that's what we mean by x sub n plus 1, that is the x value that follows x sub n. Notice the n is being increased by 1, so it's the next one. If you want the next x value, all you have to do is take x sub n minus f of x sub n divided by the derivative of f at x sub n. And this is our general formula for Newton's method to approximate the zeros of a function. Now, we do need to mention that we want this to converge. And this may be the first time you're seeing that word. It will not be the last time you see this word, especially if you're taking a Calculus 2 class. What we mean by that is when we take the limit as n approaches infinity. And what that means in the context of this problem is we take infinitely many iterations of this process, meaning we keep finding more and more and more x values. You don't just find x sub 3 and x sub 4, you find x sub 100 and x sub 1 million, and infinitely many of these x values. And when we take the limit of all of these x values, what we're hoping is that it equals some L, meaning these approach one specific finite number. So before we look at some examples, let me give you another look at what these can look like. So this is a graph of the function f of x equals, it's up here, 0.1x cubed minus 0.1x squared minus 0.2x plus 0.1. Okay. This is the graph of it. And let's say, for example, I were to start this off with an x value of, let's say, 2.5. Okay, so here's my starting x value, and we're looking to approximate the solutions to this, or the x-intercepts to this particular graph. So I'm going to hit step, and it's going to do one iteration. So there's the y value, and then the red line is representing the tangent line. So this point is now x sub 2. If I hit step again, it's going to give me another iteration of Newton's method. There's another tangent line. And notice, as we keep doing steps, it's getting closer and closer and closer to that 0. In fact, you can see the x's are starting to get extremely close together. And the more steps I take, the more x values that I find, notice eventually they just agree with each other. I can't get any more precise using this particular calculation tool. So that pretty much mirrors what we expected it to look like. Let's take a look though at what happens if I start this off with an x value of, let's say I want 1.32. Now watch what happens when I try and do Newton's method for this one. Now this one, the first tangent line takes it much farther away from the zeros. I mean, this is kind of in between two different zeros. So honestly, when you first start out, you're not necessarily sure which of these two zeros that Newton's method is going to help you to approximate. Now this took the tangent line, and my x sub 2 is now way over here. But now notice, if you keep going, it's going to go right back kind of into the last example. It's going to approximate this particular 0 for us. So just because your first step takes you farther away from what you're trying to estimate doesn't necessarily mean that these won't converge to a specific number. I mean, I can exaggerate this even more. If I give you an x value of, let's say, negative 0.58, watch what happens when I have this go through Newton's method. It goes way off screen. We can't even see how far away it goes. But given enough iterations, enough steps, it comes back to one of the zeros of this function. Let's take a look at another one. Let's say instead we look at f of x equals sine x minus 0.06 x squared. If I start with an x value of negative 2, and I start animating, notice it kind of does that same idea. It goes way off the screen. We can't even see where it goes, but eventually it does come close to one of the zeros we're trying to approximate. Notice though, it didn't approximate the 0 that was closest to my initial guess. It approximated this 0 over here instead. So you're not always sure where this is going to end up. Also, take a look at what happens if we start off with an x value of negative 3. In this case, when you start this process, it kind of gets a little bit hung up on a local maximum of this particular function. And notice it's kind of starting to not only act kind of chaotically, but it is really kind of retracing its steps over and over and over again without getting any closer to any of the zeros. This is at 20 steps, and it never got anywhere near any of the zeros or solutions of this particular function. This one does not converge to a finite number. This would be a case in which Newton's method fails. So this is what it looks like. And it's not that this happens a lot. Almost all of the examples that we discuss are going to converge to a finite number, but it can occasionally fail and not converge. So now that we have a better idea of what this looks like, let's look at some specific examples. Okay, so starting with x sub 1 equals 2, we're going to find the third approximation to the root of the equation x cubed minus 2x minus 5 equals 0. So this is an equation. This is not a function. We do need to identify our function. Our function, f of x, is going to be x cubed minus 2x minus 5. That's the function. So we're looking for the root of the equation, and the difference is the equation would be set equal to something. This would be set equal to 0 because we're looking for the root. So we've been given x sub 1. We know that x sub 1 equals 2. So what we need to do is find first x sub 2 and then x sub 3. So in general, x sub 2 would be found by taking x sub 1 and subtracting from that f of x sub 1 divided by the derivative evaluated. at x sub 1. So in other words, we need 2 minus f of 2 divided by f prime of 2. Now we've already identified f of x. What we need is the derivative of f for all x. Now the good news is this is a nice polynomial. It's pretty quick. It's 3x squared minus 2. So when we calculate this, we'll get 2 minus, when we plug 2 into the original function, we're going to get 8 minus 4 minus 5. That's going to be negative 1. And when we plug 2 into our derivative, we're going to get 12 minus 2, which is 10. So we're going to get 2 minus negative 1/10, also known as 2 plus 1/10, also known as 21 over 10, also known as 2.1. But be careful about using decimal approximations. They're fine to use as long as they're exact. But let's say for argument's sake somebody had come up with 1/3 as an answer. You would never use 0.3 in place of 1/3 because those aren't the same thing. 1/3 is of course 0.3 repeating. So now to find x sub 3, which is what we are looking for, that's our third approximation, we would take x sub 2, which is 21 over 10, or 2.1, whatever you prefer, minus f of 21 over 10 divided by the derivative evaluated at 21 over 10. So when we plug in 21 over 10 into the original function, what we're going to get is 61 1,000ths. Feel free to check my arithmetic, but that should be right. And when we plug it into the derivative, we get 1,123 100ths. So when you put all that together, you get 11,761 5,615ths. So if you want a decimal approximation for that, now this is an approximation, it's 2.0945568, etc. There's more to that, but that's it. So that's our x sub 3. And that's our answer for this one. And which answer you give is going to depend on the wording. This one I never specified whether I wanted an exact answer or an approximate answer. So this would be exact. This would be approximate. If I don't specify, either one is fine. But notice, even though we started off with a relatively nice function and some relatively nice numbers to begin with, even by the third iteration of this, or by the third step, these numbers are already getting a little unmanageable. Can you imagine if we asked you for the 20th step or the 20th approximation? So what we're going to do is give you some tools to help you out with that. Here is a video. This is Newton's method using a TI-84 calculator. Now, if you are using a TI-84, a TI-83, a TI-84 Plus, all of the keystrokes for this are going to be very similar. If you are using some other type of graphing calculator, remember to make sure you're using legal ones. Check your syllabus for which ones are allowed. Go ahead and just throw it into YouTube, put in Newton's method on a blank kind of calculator, and you should be able to find a video specific to yours. So I'm going to go ahead and play this video. If you already know how to do this or aren't interested, feel free to fast forward through the notes.
In this video, we want to use a TI calculator to help us with Newton's method on approximating a zero of a function. So what we want to do is we want the calculator to do most of the work for us instead of having to actually plug these values in and calculate them, because as we saw in class, when the functions get more complex and the derivatives get more complex, things just get a little bit messy. So we can get the calculator to do some of the work for us. That'll be really helpful. So what we want to do is we need two functions programmed in our calculator. The first function we need is the original function, and the second function is the derivative function. So if you hit your y equals button, I already program these in, but you can program the original function into the y sub 1 spot and the derivative into the y sub 2 spot. Once you have those inputted, you can go back to your main screen, and now what we want to do is we want to write a function that we can just continually iterate in order to get ourselves closer to that zero. So first thing we want to do is put in our initial guess. So if you just type in your initial guess of 1 and hit enter, that saves that, so to speak, as the previous answer in the calculator. And now to get our next guess, what we want to do is we want to take that answer, and from that answer we want to subtract the quotient of those two functions. Okay, so for the numerator there, we're going to take that old function, or the first function, so you're going to hit the vars button, go over to your y variables, select function, and you want to select the first function there, that's y sub 1. Okay, and we need to tell it what to input into that function. What we want to input is that previous answer. So that input is going to be the previous answer as well. And then we want to divide that by the derivative function. So again, you're going to go into you're going to hit your variable button, go over to your y variables, select function, and select your y sub 2. So now we're dividing that by the second function, and in that function we need to tell it what to input as well, and in this case we still want to input that previous answer. And now when I hit enter, it's going to give me my next iteration of Newton's method. So my x sub 1, my initial input was a 1. When I hit enter here, it gives me my adjusted x sub 2. So it's telling me that 1.5 is a closer estimation. And now I can just hit the enter button to do another iteration, because now 1.5 is my answer. So if I repeat that process, it's going to find x sub 3. That's my third iteration. And you can do a fourth iteration and so on just by hitting enter. And you can see that after just 4 iterations, we're very close to what the actual answer would be. And that actual answer would be the square root of 2. If you evaluate square root of 2, you can see that we've been pretty accurate with our guess just after 4 iterations of Newton's method, using the calculator to do most of the legwork for us.
So we're going to find the sixth root of 2 accurate to 8 decimal places. This one starts off a little bit different because notice you don't have an equation and you don't have a function. So what we're going to do is kind of establish that for ourselves. We know that we're looking for the sixth root of 2. So if that's what we're looking for, that's what we're going to let x equal. Let x equal the sixth root of 2. Now we want to, that kind of introduces an equation for us. And what we want to do is come up with a function that will give us this x value. So notice if we start to peel off some of the operations going on to the 2, to get rid of a sixth root, we raise both sides to the 6th power. So we get x to the 6th equals 2. These would give us the same x values. And then subtract the 2 to the other side. So what we have is x to the 6th minus 2 equals 0. And this now looks like one of the previous examples we did. We have an equation set equal to 0, and we're looking for the root of that equation. So our function is f of x equals x to the 6th minus 2, which says our derivative, this one's even better, it's 6x to the 5th power. So I also did not provide you with a starting value for this. So we're going to come up with one for ourselves. We kind of want to get a number that we think is close to the sixth root of 2. Well, we know that the sixth root of 1 is 1, so it would make sense to start this off somewhere near 1. So we'll just start there. So if we do that, in order to find x sub 2, I'll start off with this one by writing down the calculations by hand to begin with. We do 1 minus f of 1 over the derivative evaluated at 1. And again, if we do it by hand, that means we're doing 1 minus f of 1 is going to be negative 1. And then the derivative evaluated at 1 is 6. So that's going to be positive 7/6, which is 1.16 repeating. So you would definitely not want to cut this off because this is a repeating decimal. But that's where I'm going to stop doing these calculations by hand. Use the calculator to come up with the rest of them. For x sub 3, I got approximately 1.126443678. And let me write down a couple more of these, and then we'll talk about the 8 decimal places. So if you take a look at x sub 4 and x sub 5 and look at the 8th decimal place, this is the 8th decimal place in x sub 5. Notice they don't have the same number. Even if you take rounding into consideration, they don't have the same value. So what that tells me is this is not accurate to 8 decimal places. It is accurate to as many as they have in common. So if you take a look, notice right here, we start to see a difference between the 9 and the 6. These two would be accurate to within 4 decimal places. So I need to keep going. Here is my x sub 6, and notice if you go out to the 8th decimal place on this one, if you take a look at the rounding, with the 8 here, that 4 would change to a 5, which would give me agreement in the 8th decimal place. So that is our accuracy to within 8 decimal places. In other words, we know that the 6th root of 2 is approximately 1.1224620. 5. That's accurate to 8 decimal places. Let's do one more that's similar. Find x equals cosine x to 6 decimal places. So this one, we've already got an equation, which means we're going to be able to form our function. We just need this set equal to 0 because we're looking for solutions. We're looking for roots here. So we need to rethink of this as cosine x minus x equals 0, which tells us f of x, our function, is cosine x minus x, and we will need our derivative for this. So the derivative will be negative sine x minus 1. So again, we kind of need a place to start. Keep in mind your cosine function in general is always in between -1 and 1, as long as there's no number being multiplied out front. So when you take something away from that, you want it to be 0, so it makes sense to start with something like 1. So if I start with x sub 1 equals 1, 1 is not always the best choice for this. In these two cases, it has been. Also, if you start with a different x sub 1, if you were to start with, let's say, 0, you should still come out to the same answer I do in the end. It just may take you more or less steps than it takes me to get to the final answer. So for x sub 2, we're going to take 1 minus f of 1 over the derivative of f at 1. And I use calculator straight off for this one. I got 0.7503638678. Here's what I got for x sub 3 and x sub 4. Notice these only have 4 decimal places of agreement when you round on the x sub 4. So let me go out to x sub 5. So once I do that, I do have agreement definitely out to 6 decimal places. We actually have it out a little bit further. But if we want this approximated to 6 decimal places, we're looking at about 0.739085. And that's our answer for this one.